Sir, the mic is mute. A very good afternoon, a very hearty and warm welcome to you all in this popular talk series being organized by Department of Physics, Women's College, Agartala, Tripura. Before starting this auspicious occasion, I fold my hands before the light that brings prosperity, auspiciousness, good health, abundance of wealth, and destruction of the enemy's intellect. I fold my hands before the Lord, the maintainer of this creation, in the form of this light. I adore this light which destroys all the pains resulting from my omissions and commissions. Today, in this session, we are highly delighted by the kind presence of Srimati Manidepa Debbarma, Principal, Women's College, Agartala, Tripura, as the president of this session. We have with us our respected teachers from various departments of the college. We are extremely delighted with the kind presence of our resource person, the extremely talented speaker for the day. And last but not the least, we are more than overwhelmed by the presence of all the participants from across the globe who have always cooperated with us from the very beginning. Once again, I heartily welcome you all in this session. Now, I would like to request Dr. Shubrata Dev, Assistant Professor, HOD, Department of Physics, Women's College, Agartala, as well as the organizing secretary of this talk series to deliver the welcome address. Please, sir.
Thank you. Am I audible?
Yes, sir.
Respected Principal Speaker, Dr. Sachin Nanavati, Senior Research Software Engineer, Computational Wells and School of Chemistry, Cardiff University. Respected President, Srimati Manidepa Debbarma, Principal Women's College. Distinguished faculty members, dear colleagues, and my dear students. A very good afternoon to all of you. It is a matter of great pleasure that the Department of Physics Women's College is organizing this popular talk series, which will be comprising of three lectures from renowned academicians of the scientists in the month of January 2022. Today is the first one. As the organizing secretary of this talk series, I welcome our honorable principal speaker, Dr. Sachin Nanavati of Cardiff University, for giving his kind consent to be with us despite of his busy schedule. Thank you very much, sir. Dear friends, as we know, due to the outspread of COVID-19 for the last 1.5 years or so, almost the whole world is passing through a crisis, and India is not an exception. The stay-at-home orders have muddled the normal routine that we are all familiar with. All the traditional teaching learning processes have been paused since March 2020 in our country. Both students and teachers are compelled to stay at home. Presently, although offline teaching learning is going on, but still the number of offline seminar, conferences, workshops are very less compared to pre-COVID situation. Hence, to motivate the student community and also to provide them a glimpse of research in science and technology, we have initiated this program. I can say that it is a program for young UG and PG level students, teachers, and researchers. I firmly believe that during this popular talk series, we will be able to provide a unique platform for young students, faculty members, to listen to these resource persons and update their skills and knowledge. As organizing secretary, it will be a request from my side towards the registered participants, especially to all my dear students, to please listen to these resource persons. Your active participation in this will definitely motivate us to organize the same in some bigger form in the coming days. Online feedback form will be given in the Telegram group at the end of this popular talk series, that is at the end of the January 2022. And every registered participant need to listen all the talks and also submit the feedback form in stipulated time to get e-certificate. I must convey my sincere thanks and gratitude towards Srimati Manidipa Dembarma, Principal, Women's College, for her constant inspiration and motivation to all of us to organize this kind of program in a virtual platform. I give special thanks to my colleagues, Dr. Sudip Devnath and Srimati Joya Bhumik of Department of Physics, who are the main driving force for the talk series. I should also convey my sincere gratitude to Dr. Kelly Gita, Assistant Professor, and also the Coordinator IQAC, and Srimati Sharbarinath, Associate Professor, Secretary, Teachers Council, for guiding and helping me always in many technical issues. Finally, I must express appreciation to all the esteemed members of this organizing committee for their tremendous efforts. It is also my duty to convey appreciation to the technical coordinator, Srimati Pushparang Rankhal, Assistant Professor, Department of IT, for her help to organize this program successfully. Last but not the least, I am to express my sincere thanks to Ms. Ipsita Ghosh, Physics Honor Student of 5th semester of our college, for running this program in a beautiful manner. Finally, I wish for the great success of this popular talk series, and I request all the participants, especially again to all my dear students, to listen to renowned persons. Thank you once again and welcome to this talk show. Thank you.
Thank you so much, sir. Thanks for being so supportive. Now, the presidential address will be delivered by our respected Principal Madam, Srimati Manidipa Debarma Madam, Principal, Women's College, Agartala. Please, Madam.
Thank you. Hello, am I audible?
Yes, ma'am.
Respected Dr. Sachin P. Nanavati, Senior Research Software Engineer, Supercomputing, Wales and School of Chemistry, Cardiff University, United Kingdom. Research person of the today's program, academicians, my colleagues, and my dear students. Good afternoon. In this popular talk organized by Department of Physics, Women's College, Agartala, Tripura. We are highly privileged with the kind presence of Dr. Sachin P. Nanavati from Cardiff University, UK. I, on behalf of Women's College and on my own behalf, heartily welcome you, sir, in this program. I welcome all faculties, research scholars, and students from different parts of the country who are joining us through StreamYard. Being the principal of Women's College Agartala, let me introduce our college to all of you. Established in 1965, it is the first college for women in Tripura, imparting quality education exclusively for women. Being a government college under the aegis of the Department of Higher Education, Tripura, and having 22 academic departments under arts and science disciplines, it is contributing significantly towards women education through a holistic and meticulous academic curriculum. During the last 2 years, we were compelled to adopt online programs, and our college have conducted many webinars, popular lectures during this time. Today, Department of Physics has taken this initiative to organize this popular talk. It is our proud privilege to have Dr. P. Nanavati, who will be talking about computational science, perspective, and future opportunities. Computational science is a rapidly growing field which utilizes advanced computing capabilities to understand and solve complex problems. It is not limited to any one sub-discipline of science, but is being widely used in physics, chemistry, mathematics, biology, art science, etc. The main objective of this talk is to create awareness among the students about the recent scope of research as well as to give an idea of the ongoing research in the field of physical science. Besides this, students can get a platform to interact with the eminent person in the field of science and technology. With these few words, I would like to welcome Professor P. Nanavati again, and I am sure we will be enriched by his speech. Thank you. Thank you all.
Thank you so much, madam. Thanks for always motivating us to do the best things. For the last 2 decades, it has been observed that there is a slow decline in the number of enrollment of students in undergraduate science subjects. It affects both quality as well as quantity of students pursuing higher education. This is primarily due to the shrinkage in the job and future scope of education and research. Conducting such a popular talk series will make a positive change in the mindset of both students and the teacher community. Main objective of this popular talk series are creating awareness among the students regarding possible scope of research in the field of physical science, highlighting the scope of future education to elucidate the various ongoing research topics, create a platform for the students to interact with the eminent person in the field of science and technology, facilitate opportunities for networking collaborations and exchange of ideas with eminent academicians of the nation and abroad, and to boost young researchers and faculty members towards research and development. And now, this is the time for the much awaited session where the extremely talented resource person will share his valuable words in this talk series. We have with us Dr. Sachin P. Nanavati, Senior Research Software Engineer, Superconducting Wells and School of Chemistry, Cardiff University, United Kingdom. Dr. Sachin has more than 18 years of diverse international experience working in both academia and industry. He specializes in scientific software development, high performance computing, HPC, and computational material science. He has published his research in leading journals including Physical Review B, Journal of Physical Chemistry C, and Applied Catalysis B. In the last 4 years at Cardiff University, he is combining his experience in parallel programming with a detailed understanding of research in the field of computational chemistry to translate research needs into HPC applications. Prior to that, he was a joint staff member at RWTH, Aachen University, and Julius Supercomputing Center in Germany, Senior Technical Officer at Center for Development of Advanced Computing, CDAC, Pune, and Project Associate at Physical Research Laboratory, PRI, Ahmedabad. Academically, he obtained his MSc and PhD in physics from University of Pune and MTech Computational Techniques from University of Hyderabad. Today, we are fortunate enough to have Sir with us. Please, sir, platform is all yours.
Thank you very much. Can you hear me well?
Yes, sir. Yes, sir.
Okay. Can you see the slides? Can you see the slides?
No, sir. I'm not saying.
Okay. I will share it again.
Yes, sir. Yes, sir. Now it's visible.
Now it's visible, right? Yeah.
Yes,
Okay.
sir.
And I will just go through one or two slides. Can you see the change in slides?
Yes, sir. Yes, sir.
I think thank you very much for the kind introduction and giving me an opportunity to interact with students and faculty members of Women's College Tripura. I just felt that I should have been there, but unfortunately, due to prevailing pandemic, we are unable to travel at will. At the same time, good afternoon, everybody. Again, thank you very much for giving me this opportunity. And today, I would like to talk about what are the perspectives of computational science. I purposefully put it as computational science, so it's not just restricted to physics or chemistry or mathematics, as the principal madam rightfully said. This talk would be all about computational science, which is now emerging as a leading discipline across all domains. It is a ubiquitous discipline. You will find computations not just in natural sciences, but in engineering and even humanities. So this field is growing, and I think it requires talented students and future researchers like you to lead this domain into a more concrete branch of science. Today's agenda would be I would briefly touch upon what is computational science. We'll see an example, an everyday life example of how to translate a given mathematical problem into a computational problem. Then, to elaborate more, we'll see how to solve the well-known many-body Schrodinger equation. We'll see that it's impossible to solve it without computation and without further approximation. In particular, we'll look at a very successful theoretical development called density functional theory. We'll also see that DFT cannot be solved with ordinary computers. We need supercomputers to do the calculations. We'll also see a very brief application of DFT to coordination polymer. Not but lost, at the end we will have some future prospects where this discipline can lead you to, how to go about it, sharing my own experience, and of course we'll take some question answers at the end. I just request the coordinators to like, if you have any questions in between, you can just type it on the chat box, and maybe the coordinators can just tell me at the end so that we can answer it one by one. Okay, so what is computational science or computational physics in general? It is basically an art and science, I would say, of solving physics equation. Most of the time, we already know the well-known physics equation. It could be Newton's equations, it could be Schrodinger's equation, but then we are used to solving these equations using pen and paper. That means in analytical manner. However, for practical applications, we cannot solve these equations for large number of say atoms, large number of ions, and so on and so forth. So for that, we have to translate this physics equation or a mathematical equation into an equivalent computer program which will do the calculations for us and validate the results. So to do this, we employ numerical methods, different numerical methods. We'll see one of them today. Not just that, once we know the numerical method, we should also use a computer program which would help us achieve our goal. And then we'll see that in most cases we try to solve the problem approximately, not very accurately. However, it is more than enough in most of the cases to solve this problem approximately so that we get desired results. So let us start with our usual mathematical technique, integration and derivatives. We all know about it. We have been doing it for last 3 or 4 years. Maybe starting from your 11th standard, you must have done derivatives and integrations. So what is integration? Integration, on the right hand side, what you can see is nothing but we try to find out the area under the curve. Here we have a function f of x, which has a lower bound b and an upper bound c, and then there is a function f of x given. It could be any function, a well-behaved function, and then we would try to find out the area under the curve, which is basically which has a lower and upper limit given respectively by b and c. So this is what integration is all about. At the same time, derivative is nothing but we find a tangent at a point a, and that tangent will give basically the meaning for derivative. Let us look a little bit more into an integration. So as we said before, integration is basically an analytic expression where we write a function and then we integrate between two upper and lower bounds, and correspondingly, it's basically the area under the curve. So computationally, if you want to calculate an integration, what we'll do is basically try to estimate the area under the curve for a given function. And how can we do that? Okay, we do it something with the help of something called trapezoidal rule. Now, what are trapezoids? Trapezoids are basically geometrical objects which has two parallel edges. So, for example, this line and this line is parallel at the most two edges. In many cases, it could be three, but at the most, it should have at least one parallel edge. Now, what we have done here on the left-hand side is that a given function f of x, which is shown in black line, is basically discretized at 4 points. So starting between A and B, we are discretized at 4 different points. And then we consider the area under the curve for each subdomain. So our hope is if we basically add the trapezoids together, we might get a good approximation to the total area under the curve, and that means the integration which we are doing. There are two things in this when we integrate. The first of all, the step size delta x. So delta x is basically an equal step size with which we divide the range between A and B. Here, for example, we have 4 steps. We have divided our interval into 4 equally spaced step size delta x. So we say A, then A plus delta x, A plus 2 delta x, and so on and so forth. So any ith trapezoid, any ith equation, any ith trapezoid is nothing but the difference between f of xi and f of f of I minus 1, that means the previous one, and then we divide it by 2 because we always consider the mid value between these trapezoids. So and then we have to multiply with the step size delta x. So the approximation is very sensitive to the step size delta x. So if we take a very large step size delta x, we might not get accurate result. But if we choose a smaller step size, there is a possibility that we might get a good result, a good approximation. However, while doing that, we'll see that we do more computation. So it's a trade-off. Similarly, so for the entire curve, we can say that the area under the curve would be the value of the function at, say, x naught, at x1, x2, x3, x4, and so on and so forth. We'll add all those values and divide it by 2, and of course we'll multiply by the step size. So this is how we'll get the answer for our integration through a numerical method. But how to convert it into a computer code? Before diving into a computer code, we should understand something about a pseudocode. You might be knowing that there are different computer languages. It could be C, C++, Fortran, Python, and so on and so forth. However, mentally, we should have a pseudocode. A pseudocode is basically a code based on which we can write a real code, a real computer code. So pseudocode cannot be implemented, but it's a mental picture which will give us step-by-step direction of writing a code. So what it says, like we'll see that the first step is start. Okay, we'll start the computation. Then we'll define a function. So here, for example, it could be a sine of x or sine plus cos of x and something or some more complicated function, which is shown by the black line f of x. Once we have defined the function, we have to understand 3 quantities: the lower limit a, because my function starts from a, my integration is basically from a to b, so lower limit a, upper limit b, and then I have to decide my step size delta x. Once I know all these 3 quantities, I will calculate the step size delta x, which is nothing but the lower limit minus upper limit divided by the subintervals. So here, for example, I have divided my total intervals into intervals in 4 equally spaced subintervals. So now I have these numerical values in place, and with that I will start my integration. So my first integration would be the first trapezoid, which my cursor is showing. So what is this first trapezoid? It's basically the lower limit, the functional value at lower limit, then the functional value at say the upper limit here, and this is my the most crudest or approximate value for my integration. After that, I have to do a loop. Now, what a loop will do? I will have a loop index. Say it starts with from 1. In this case, it will go from 1 to 4 because I have divided my intervals into 4 equally space values. So the loop index will go from 1 to 4 here in the present case. So I will start with the lowest limit. So my lowest limit is A, and then I will go on increasing my loop index. And the way to do it is nothing but I will always multiply my current index with the step size, and it will always start from the lowest limit. With this, I will start my integration, and then after I do my first trapezoid, I will go to the next one, next step. So I will increment it by 1, and I will do this loop while I am inside my subinterval. That means between A and B. So once I do this, I get an approximate value for the integration. I will print the result. I will validate it. For example, I will start with a known function, say sine of x or cos of x. Because I know the analytical integration value of this function, and I will see my code whether it gives the correct value for that. Once I'm satisfied, I can say that yes, this code gives me correct results. And of course, the next task for the computational scientist is translate this pseudocode into a working computer code. It could be, as I told you, it could be in C, C++, Python, Fortran, and so on and so forth. So this is what a computational scientist has to do. As you saw in our previous case, we had divided the interval into 4 subparts. But who stops you from doing just 4? Let me go for 8. So n is equal to 4, n is equal to 8. As I told you, with n is equal to 8, I will get more accurate result. With n is equal to 16, I might get even more accurate result, but I will end up doing much more computations. So there is always a trade-off. So when I increase my step size, I will most probably get more accurate results, but in fact, I will end up doing more computations. So I have to find out a good balance. I'll check it out for n is equal to 8 and n is equal to 16 and see the end result and how, and then estimate the error between these two values. And if the error is not changing much, I will go for n is equal to 8 because it gives me reasonably accurate result, and at the same time I have reasonable computational time which I can spend on doing that. So this is a trade-off which one has to do. So in summary, what we have done is we have translated a physical equation, a mathematical equation, into equivalent computational model by writing a pseudocode. While doing that, we had to design a code, so which will implement and validate the function, the mathematical function which we want to solve. But for doing that, we had to use a numerical method. For example, in our integration case, we used a method called as trapezoidal rule, and we use this method for formulating and designing and of course interpreting this computer model. At the same time, we should be clear whether our answer is correct or not. For that, we have to do visualization. So we can plot the result, we can have a 1D, 2D, 3D plot, and then we can test our hypothesis. And after doing all these things, what we do, which is most important, is connect our results with the theoretical or experimental understanding, and that's why simulation has become a third domain in scientific research, apart from theory and experiments. Now the question arises, to achieve this goal, what are the skill sets required for a typical computational scientist? The first and foremost, as you could see, is the so-called algorithmic thinking. Remember, we wanted to do an integration. So we always have been taught to do integration with the help of pen and paper. That means analytical solution. But if we want a computer to do that, we should think algorithmically. That means we have to first of all have a pseudo algorithm in our mind, which we looked at. Not just that, the heart of that pseudo algorithm was the numerical method which we employ for example, the trapezoidal rule. And then why we are doing all these things? Because we want to understand the science behind doing that, because we want to apply this method for a particular scientific problem. So we should have we should know the scientific problem also correctly. And in future, and when you practice it, you will see that not just science, but we should always use this technique for some societal benefit. So what we have done is we have converted our mathematical problem into a step-by-step procedure, which the computer can implement. But while doing that, nowadays it's not any software development cannot be done in isolation. That means one or two people cannot do it alone. It's always very important that we communicate our results and issues with other people, our colleagues, our co-workers, and so on and so forth. So not just having analytical skill, not just having a good computational skill, that means programming skill, but also one should have a proactive communication. We should be able to express our views, both written as well as written, as well as in presentation mode, and all these platforms proactively, so that others know what are the issues. Most of the time, it's an experience that we cannot understand whole issues correctly. So we always look around, get help from people in writing and running the code, or even Google the questions which we have, because the assumption is that the problem which we are facing, the similar problem somebody else might have faced somewhere else, and he or she might have written a blog explaining how to go about it. So that's very important. And then, of course, we'll have a visualization of data for validation. Okay. So now we have got a good glimpse of what computational science is all about. A fairly good, reasonable glimpse. Now let us use this technique to address a problem. The problem in which I am interested, I'm working right now, and that's called the electronic structure problem. What it means is that generally it is basically a dream of a physicist or even a chemist to basically predict the properties of material, or to understand the properties of material, just by knowing few important parameters. For example, if you give me a system, I will ask you a question. Okay, tell me what are the types of atom. That means the atomic number Z. How many number of atoms of each species are present? Can you also tell me the XYZ coordinates of those atoms or ions? And can you also tell me the cell dimension, whether it is a body centered cubic structure or a face centered cubic structure, and so on and so forth? If I can solve this problem, that means predict the properties of material by getting only these fundamental parameters which we discussed before, then these methods are called ab initio. Ab initio is a Latin word which means starting from scratch or starting from beginning. In other words, it means we are making as less approximations as possible. The other name for this technique is also first principle approach. So theoretically, we make no approximations, but as you will see, it's not possible to do any like we cannot solve equations exactly. We need to do some approximations. Of course, they are physics based, so we know what approximations we are doing, and those approximations will result in the corresponding error. So we have a fairly good idea of what the errors it might have. So as I said, in practice, we'll make a reasonable approximation, and we'll use this method to solve a many-body Schrodinger equation. To keep case simple, we'll concentrate on time-independent and non-relativistic Schrodinger equation. Now, this is the well-known eigenvalue problem, which we see in physics and chemistry textbooks. H psi is equal to E psi. Now, what is H? H is my Hamiltonian operator. We'll see what it means. Psi is my wave function. Okay, and then this E is nothing but my energy eigenvalue. So it's wrong actually. These it should point out to E. So energy eigenvalues. So I'm solving this eigenvalue problem. So what is Hamiltonian? Hamiltonian, as you know, is basically made up of kinetic energy part plus potential energy part. So the first part here, it's basically the kinetic energy of electrons. We are concentrating only on the electronic problem. So we are neglecting the bulky nuclei. with the help of something called Born-Oppenheimer approximation, because we know that electrons are or the nuclei are at least 1836 times heavier than nuclear than electrons. That's why we'll just ignore the motion of nuclei and just concentrate on electrons, and that's why the name electronic structure calculation. So the first part, as you saw, it's basically the kinetic energy of electrons. The next two parts are basically the potential energy. Again, we have divided into two parts: electron nuclei interaction and electron electronic interactions. So if we could somehow plug the values of potentials, different potential as well as kinetic energy part, and then operate on wave function, we'll get the energy eigenvalues. And once we have the energy eigenvalues, in principle, you can predict all the properties of material. But there is a problem. The problem is my wave function, many body wave function, because in one mole of a given substance, there are Avogadro's number of atoms, 10 to the power 34 atoms. So it's impossible. So this my many body wave function is basically a function of all the atomic coordinates of all the atoms, and then so this is basically a function of 3n dimensional coordinates, where n is the number of electrons. And it quickly turns out that it becomes a useless problem, because we cannot solve this problem because the dimensions are so large that even the most powerful computer available currently cannot solve it. Let us take an example. Just let us look at a simple carbon dioxide molecule. So carbon has 6 electrons, oxygen has 8 electrons, and we have 2 oxygens. So in all, we have 22 electrons. So if we write the Schrodinger equation without making approximation, so we have to solve a 66 dimension function, because each electron will have 3 coordinates, x, y, and z. So that's why 22 into 3. So we will have to solve a 66 dimension function. A simple 100 platinum atoms, which is very common, will have 23,000 dimensions. So it's impossible to solve this Schrodinger equation. So what we do is an approximation. The first approximation is nothing but Hartree product. That means we say the total wave function is nothing but the multiplication of individual wave functions of each electrons. So that's what my psi would be, the psi of R1 multiplied by psi of R2, and so on and so forth. That means I'm basically ignoring the electron-electron interactions, which look absurd, but we'll see that helps in solving the equation. So even with such a large system, we are unable to solve the Schrodinger equation. Then came in 1964 the most famous density functional theory. So there are two equations, two essential algorithms given by Hohenberg and Cohen, and then by Cohen and Sham in 1964 and 65 respectively. I won't go into the details, but I will just like to emphasize the central theme. The central theme is that the Schrodinger equation is not basically a function of wave function, the vector quantity which has 3n dimensions, but a quantity called electronic charge density, which is basically a scalar quantity shown as rho of Ri. And my energy is basically a function of charge density rho, which in terms is a function of the coordinates Ri. That's why that means E is a function of rho, which is a function of Ri. So that's why it's a function of a function. That's why the name functional. And we can see that with density functional theory, my Hamiltonian is basically reduced into a kinetic energy part and an effective potential, which is basically composed. Again, the effective potential is basically composed of electron-ion interaction called the Coulomb interaction, the electron-electron interaction, and something called the exchange correlation. So if I can solve this example for each electron, because I have used the Hartree approximation, I can have some, I can, in finite amount of time, I can predict the properties of material. As I told you, DFT was highly successful. Professor Walter Cohen, who developed this theory, got Nobel Prize in Chemistry in 1998, along with Professor John Pople, who wrote computer programs to solve this method. Okay. Now comes the question of how to solve it. And here comes high performance computing, that is parallel computing, into picture. As we saw, the Hamiltonian, for even a simple molecular case, which we'll see of silver coordination polymer, the Hamiltonian or the matrix size is 3 lakhs by 3 lakhs. So I had to diagonalize that matrix. So even on a most powerful laptop or a desktop machine, it will take days to solve this. And most of the time it wouldn't be possible because we don't have enough memory for to solve it, because we are solving this eigenvalue problem at size equal to each side. So for that, we need supercomputers. Now, supercomputers are basically this is a diagram which you can see. Even your laptop or even your mobile phone is a kind of mini supercomputer. Each supercomputer has several nodes. Each node will have several cores. For example, our current machine has maybe 4 cores or 8 cores, so several cores, and then they will have some memory, and then all these nodes would be interconnected through a fast connection, so that each core of each node can talk to any other core of any other node. And this is what a supercomputer in short is all about. uh, so this is a new supercomputer which was established around 2 years back at Banaras Hindu University. This is one of the fastest supercomputer in the world. It's Fugaku in Japan. So this computer has around 72 lakh cores. Okay, so much. And all cores can talk to each other. This is a relatively old machine, Paramjiva 2 at CDAC Pune, which even Subrato Day is using these days. And I had used it when I was in Pune. A very fast machine has been installed recently in University of Edinburgh in UK. This is a national facility called Archer 2, and I'm actively using this supercomputer for my calculations. Okay, so now we have understood what is computational science. Then we have a problem in hand, that is solving the many-body Schrodinger equation using density functional theory. We know the tool. The tool is high-performance computing machine, that is a supercomputer. Now let us come to a problem. Where could we use this all these techniques which we have gathered till now for a problem in hand? So today we are going to look at a problem of silver-based coordination polymer. So this is basically a polymer which has inorganic and organic ligands. So inorganic part is basically the silver oxide ions, and organic parts are basically the ligands. Here you can see a benzene type of ligand. It's called benzene dicarboxylate. So this is a hybrid material which has inorganic like metal as well as organic ligands. And these materials right now are gaining a lot of importance because we can tune the properties of materials and get desired properties. And currently we are using this material for photocatalytic degradation of organic pollutants. This work is being done with our experimental collaborators at Indian Institute of Technology, Kharagpur. Okay, so what is this material all about? So a unit cell of coordination polymer has 36 ions. It has 4 silver, 16 carbon, 8 hydrogen, and 8 oxygen atoms respectively. So this is the problem which we want to solve theoretically. Our aim is, can we predict the properties of these materials even without doing experiments? And the answer to this, okay, before that, as I told you, we call these methods as ab initio or first principles, because we just need basic parameters. For example, the crystal structure of this material, here it is a simple monoclinic. Then the lattice vectors ABC, you must have studied that lattice vectors in your solid state physics course. Then the angular part, the angle alpha, beta, gamma of my crystal structure. Then the XYZ coordinates of each ion. Nowadays, you can get all these information from a database. For example, the Cambridge crystallographic database. It's free; one can download it. And the current material has this nomenclature CCDC, and this is the number. So with this number, I can download the structure of silver-based coordination polymer, and we already seen its composition before. So from this CIF file, crystallographic information file, I get all the parameters. That means the XYZ coordinates, the size of a unit cell, and so on and so forth. So my question is, can I predict almost all the properties of material? Here we are talking about periodic solid. The answer is more or less yes. We can, for example, we can find the properties of material like mechanical. We can find out the Young's modulus, the bulk modulus. the electronic structure which will shed more light on density of states, band structure, and so on and so forth. We can predict the optical gap of material, and most importantly, we can compare with experiments. So with reasonable accuracy and with reasonable computing power, we can match our results with experiments. And not just that, if our simulations are of high quality, we can predict the properties, even those properties which experimentalists haven't verified. Okay, so now some results. I'm showing the density of states for this material. So what is density of states? The density of states is nothing but it's basically a frequency distribution. On x-axis we have the energy, so energy in range E and E plus delta E. We'll find out some delta E, and then in that energy range we are trying to find out the number of electrons of one particular atom, say hydrogen, oxygen. Not just that, but each orbital, that means s orbital of hydrogen, the 2p orbital of oxygen, the 2p orbital of carbon, and so on and so forth, and even the silver one. So we can decompose my electronic structure into different ionic contributions, not just that, into the orbitals of each ion, and so on and so forth. Here you can see at 0 electron volt, this is the conduction, this is the valence band maxima shown in dotted line, whereas the conduction band minima is at plus 4 electron volt. Now I can see that my valence band maxima is mostly composed of 2p orbitals of carbon and oxygen, which hybridize with the 4d orbitals of silver. So with this, I can tell the experimentalists like how the charge transfer is going to happen. So my electron, which mostly would be 2p orbitals of carbon and oxygen, would be excited to valence band to conduction band minima, which is mostly composed of 2p orbitals of carbon. This is the charge density plot. You can see the red atoms are oxygen, the brown atoms are carbon, and the silver atoms are basically the gray atoms are silver. So you can see that most of at valence band maxima, most of the charge is basically on the 2p orbitals of oxygen. You can see this double dumbbell shaped orbital. Again, there is a 2p orbital of carbon because this is the benzene ring, and there is some contribution from the d or 4d orbitals of silver. Whereas the conduction band minima is mostly the delocalized charge on the benzene ring, that means the 2p orbitals of carbon. So this is the information which you can pass it on to experimentalists. But the problem, one of the problem here was that my band gap of my material was around 4 electron volt. 4 electron volt is nothing but, if you compare it with solar spectrum, it comes in ultraviolet region, UV region. So we know that only 4% of solar spectrum is composed of UV region. If I want to, but so that means my theoretical efficiency of this material is just 4%. My whole aim is to narrow this band gap and make it into visible range, because 44% of solar spectrum is in visible range. So how to do that? So what we did was we replaced one of the hydrogen atom in the original structure with amine group. Amine is NH2. So one hydrogen would be removed, and I will place NH2 at this location. Okay, you can see here, this is NH2 which has been placed. And this simple modification, of course, experimentalists had to work really hard to do this, but computationally it is very easy. But we showed that with this simple modification, we basically lower the band gap of material and make it into visible range. So on the left hand side, this is the parent photocatalysis, which we discussed earlier. The band gap is around 3.7, and visible light, this material cannot absorb visible light because the band gap is much more larger than the visible light. However, with modification, that means amine modification, what happens is there is a band which is created around 0.8 electron volt above valence band maxima, which reduces the band gap from 3.7 to 2.9 electron volt, and now 2.9 electron volt comes in visible region, and now my efficiency of the material has increased many-fold because it can not only absorb UV light but also visible light. So this is the important thing which simulation can shed results even before doing experiments. Okay, now let us come to the future prospects. So we have seen what computational science is all about, the pseudocode, the programming skills, then application of this computational science to a problem. In particular, we looked at many body Schrodinger equation. Okay, but after you must have you must be wondering, like, after doing all these things, what are the future prospects? Because I guess you are all doing undergraduate studies, like that means you are pursuing your BSc. So if somebody of you, if you think that, oh, this is an interesting area and I would like to pursue it, so how to go about it? How should I do? So most probably there are two streams which I see. If you're really interested in the in the computation aspect, the computer science aspect of it, I will advise you to go for Master of Computer Application (MCA), because that will give a glimpse of computer science and related IT techniques. So you can just pursue a 3 years MCA after your BSc, or if you think that you are interested both in the computation as well as the underlying science, then I will advise you to pursue MSc, which I did, for example. You can do it your MSc either in physics, chemistry, maths, statistics, and so on and so forth, the area in which you are interested. And there are several universities which offer computational physics as one of the specialization. For example, my alma mater, University of Pune, they have a very good course on computational physics. University of Hyderabad, again a very good central university. Jawaharlal Nehru University, and most of the central universities, including Tripura University. I have seen the course of Tripura University, MSc Physics course. They have a computational course which has thrust on numerical analysis and Fortran programming. So this is also, you can even join Tripura University, which is again a central university, if you are interested in pursuing both science as well as computation. Many of you would find that even after doing MSc, it's not enough. Few of you would be motivated to do further studies, for example, being a PhD in computational physics or chemistry, and that will enhance your skill sets, and you can target a particular area which you are interested. It could be condensed matter physics, or it could be say high energy physics. It could be computational chemistry, and so on and so forth. Now let's come to the job opportunities. As we saw, it's a computational science is a specialized area. So of course, relatively there are less jobs as compared to say IT. There could be less jobs, but since it's a specialized area, if you have a good skill, both computation as well as scientific understanding of one particular domain, chances are that you might get a good opportunity in that narrow field. From my experience, I can say that there are opportunities both in academia and industry. Nowadays, a lot of industries hire computational scientists to carry on their work. For instance, you must be knowing the vaccine which has been given in India. I think the Covaxin and Covishield. So Covishield was AstraZeneca vaccine, which was developed in Oxford University. So there were a lot of scientists who did the wet lab experiments, but at the same time, there was a sizable number of computational chemists who arrived at a given formula doing computation. So even this area requires a lot of people with expertise in computation. Finally, I would say something about research software engineering. I'm a research software engineer here at Cardiff University. This is a new branch which has emerged maybe around 8 or 9 years back. So software engineering could be found in many industries, in many IT industries. But research software engineering is basically a specialized branch where we use software engineering skills to solve a scientific or engineering problem, because it requires more understanding. You should be good at programming and related things, but at the same time you should know the science and engineering aspects of a given problem. So there are growing opportunities to become a research software engineer as well. Thank you. Thank you very much for your kind attention. Let me take up some questions if there are any. I will also circulate these slides. I will send it to Shubrata Day, and he might. So you will have a copy with it. So if you want to go through it again or look at some references, there are. You don't have to. You don't have to look around. This could be as a reference material. Thank you very much.
Thank you so much, sir. We are really humbled for your valuable talk. Like it was really amazing.
Thank you for your wishes.
Yeah.
If there are any questions, I would like
Yes,
to.
sir.
Yeah,
Yes, sir. Yes, sir. There are two of the questions.
I think I will just stop sharing my screen.
Yes, sir.
Just a minute.
So the first question says,
Yeah,
does the study of computational science depends on the advancement of computer science theory?
yeah, this is a very good question. Actually, both the fields go hand in hand. As I said, what we are trying to attempt is solve a physics equation or chemistry equation, which is already known. So Schrodinger equation was given almost 88, 90 years back. Okay, but as has been pointed out, computer or basically computing's infrastructure is growing day by day. So many of you must have heard a famous law called Moore's law. So Moore was one of the person who started this Intel company. So what he said was the computing architecture or the computational speed doubles every 18 months. So every 18 months, we went from Pentium 3 to Pentium 4. Now we have many core systems, Xeon systems, and so on and so forth. So we have to match our software to emerging hardware, to ever changing and emerging hardware, and that's one of the key challenge here. And that's why computational scientists would always be in demand, because we have to modify the code. We have to see that the same code gives the same answers on different computing platform. It is more efficient. The same efficiency has been maintained, and that requires a lot of tuning, understanding of both computer science as well as computational science as well as physics and chemistry. So that's why this because of this, we see that computational scientists are in demand. So of course, it's a very true thing. We have to always tune and modify our code to meet the current hardware.
Yes, sir. Yes, sir. One more question. I think theoretical science models can well be executed, but how the practical science model will cope up with the computational science?
Yeah, yeah. So as we looked before, we cannot solve any equation exactly. We always make approximations. So when we make approximation, we know what kind of error might creep into my answers. For example, when I'm solving Schrodinger equation via density functional theory, there are two quantities which I had briefly mentioned: exchange and correlations. So those are basically quantum mechanical calculations. Quantum mechanical entities, they don't have any classical physics analog. My accuracy of my calculations are totally dependent on the kind of exchange I take, the kind of correlation I take. So whenever my results doesn't match with experimental results, I know why it is so. It is because the errors which I make while approximating correlation, mostly correlation or exchange. And now, to match my results more and more with, say, the practical answers, the experimental result, I try to improve my approximations in exchange and correlation. So this is how it goes on. So it's basically one leads to other. Sometimes the experiments are ahead and and simulations follow them. Sometimes, for example, in the test case which I showed, the latter test case which I showed, simulations go ahead and then they guide the experiments. Okay, go in that direction. For example, do amine functionalization, and you might reduce the band gap. Yes. So this is how it's an interplay between both the domains.
Okay. Thank you, sir. This was two of the questions from our side, and it was really amazing, much informative, and at last, thanks for sharing your valuable time with us.
Yeah,
Thanks a lot, sir.
thank you for it. We have a Christmas break right now, so that was not a problem. And thank you for organizing the event. If students have any further follow up questions, you might even write down. I had displayed my mail ID, or you can give it to Shubrata, who can forward it to me, and we can even discuss further.
Surely, surely, sir. Surely, sir.
Yeah. Thank you very much for the opportunity to speak to interact with so many bright minds. Thank you.
Thank you, sir. Now I would request Dr. Shudeep Dipnath, Assistant Professor, Department of Physics, to convey the vote of thanks.
Am I audible?
Yes, sir.
Okay, thank you, Shida. Thanks, Dr. Subrodev, sir, for giving me the opportunity to give the vote of thanks. I like to thank Dr. Sachin Nanavati, Senior Research Software Engineer, Supercomputing, World Science School of Chemistry, Cardiff University, United Kingdom, for his innovative and popular lecture on this topic. Computational science, perspective and future opportunities. Thank you, sir. You have given an immense awareness among the students regarding the scopes of higher education and research in the specific field. They have got the platform to interact with the eminent person in this field of science and technology like you. After your fantastic lecture, you all, including the students and all other participants, are now understood what is the role of computational science in the physics and chemistry, starting from Schrodinger equation for predicting the properties of materials. You have also shown the gateway and career opportunities to become a successful computational scientist. Thanks a lot, sir, again. Now I'd like to thank Srimati Mandika Devarma, Principal and also the President of the program, for her constant encouragement to hold such type of motivational popular talk in our college. Thank you, Madam. Again. Now I'd like to thank Dr. Subrata Dev, Assistant Professor of Physics Department, Women's College, Organizing Secretary and also the History of Physics Department, Women's College, for nicely organizing the popular talk of unique topic by an eminent person to boost our beloved students, to motivate them to show a proper track of higher education, research and career opportunities. In future, we hope we will get again such type of opportunities. Thanks a lot, sir. Again. At least, at last not the least, I'd like to thank Srimati Pushpa Rankal, Assistant Professor of IT Department of Women's College, Technical Coordinator of the program, who supports technically in all ways to hold such type of program. Thanks a lot, madam. Finally, I'd like to thank all the members of the organizing committee and also the participants, students, especially Ikshita, for their constant support. Thanks a lot.
Thank you so much, sir. Thanks for being so supportive. Here, the popular talk series comes to an end. Thanks for the patience. Thanks for hearing. Thanks a lot. Stay connected. Have a great day. Bye.
Thank you very much. Have a nice day ahead. Stay safe. Bye.
Yes, sir.